Number 25 says, how many resonance structures, if any, can be drawn for the N2O4 molecule? Since they're asking about resonance structures, we have to draw our base structure first. In order to do that, we first have to figure out how many electrons are in the entire molecule. So we have 2 nitrogens, and nitrogens have 5 electrons each, because nitrogens have 5 protons, and in order to be a neutral atom, they have to have the same amount of electrons as protons. So they have 5 electrons. And oxygen, since they have 6 protons, they also have 6 electrons. Since we have 2 nitrogen atoms, we have to multiply this 5 by 2. So that gives us 10 electrons from the nitrogens. And we have 4 oxygen atoms, so we have to multiply the 6 by 4. This gives us 24 electrons from oxygen. And then if you add that up, that becomes 34 electrons total. Or as I like to do it in pairs, that means 17 electron pairs. So now that we have the amount of electron pairs, we can start building our structure. So first, we have to connect all of the atoms some way with some bonds. So I'm going to connect my 2 nitrogens, connect the 4 oxygens, and this is what I like to call our base structure. So you have all the atoms and they're connected somehow by these bonds. So we said that we can use up to 17 electron pairs total, and we've used up 1, 2, 3, 4, 5 pairs to connect them all. So now we can distribute the rest of the pairs up to 17 to try to fill their octets. So first I'm going to give electrons to the more outside atoms, which are also the more electronegative atoms, so that would be oxygen. So we have 1, 2, 3, 4, 5 pairs. This is going to be 6 pairs, 7 pairs, 8, 9, 10, 11, 12, 13, 14, 15, 16, and 17 pairs. So if we look at the structure, each of the oxygens have a complete octet. They're all happy, they all have 8 electrons, but the nitrogens, they only have 6. We need to complete their octets. But we don't have any more electron pairs because we already have 17 electron pairs. So in order to give nitrogen a complete octet while maintaining the complete octet of the oxygens, we're going to take some of an oxygen's electrons and share it with nitrogen. So pretend we can take this pair, put it next to that bond, this pair, put it to that bond, so then that's going to give us this structure where we have some double bonded oxygens to the nitrogens. Well, this one is single bonded, this one is double bonded, single bonded. So now, when I redraw my structure, oops, that one's not supposed to be there. There we go. So now if you look, each atom has a complete octet because this oxygen has 1, 2, 3, 4 pairs of electrons, 1, 2, 3, 4 pairs, 1, 2, 3, 4, 1, 2, 3, 4, and then the nitrogen's 1, 2, 3, 4, 1, 2, 3, 4 pairs of electrons. So now they're all happy, they all have a complete octet. Now we can actually start looking at the resonance structures. So we know that every time you see a molecule with a double bond or even triple bond, we know that they have resonance structures because these electrons don't just stay local to this atom. They actually travel all over the electron cloud of the entire molecule. So that's what gives rise to resonance. It's because these electrons, say this double bond, it doesn't always stay there. Sometimes those electrons can jump from this bond between nitrogen and oxygen to this bond between nitrogen and oxygen, and it can travel all the way around the molecule. So instead of this just being one structure, this molecule can look like this. instead of, say, this oxygen having a double bond, that one can be single bonded, and then that double bond can move to this oxygen. And then complete the octets. So now you see that this molecule can look two different ways because this double bond moved from here down to there, so which would make this structure. Now those double bonds can also jump from these atoms to the top atom, so then that would look like this. Two nitrogens. So if the double bonds move from the bottom atom oxygens to the top oxygens, they look like this. Again, you want to complete your octets to make sure we always have 17 pairs. So now from this molecule to this molecule, our double bonds moved from the bottom oxygens to the top oxygens. And then there's one more combination that we haven't done yet, and that's when these double bonds move from these two oxygens to these two oxygens. So now we're going to have these oxygens double bonded and these ones single bonded. Again, complete your octets. So now you can see that these double bonds have shifted. When they're in this diagonal, they can be in the same plane, in the same direction here. They can also be at the upper oxygens, and they can also be in this diagonal this way. So again, resonance occurs due to the delocalized electrons, because they don't just stay within the vicinity of one atom, they can travel all around the entire molecule, and that's what gives rise to resonance structures. So here we've just drawn all possible combinations. We can't draw any more different molecules with these double bonds in different places. Well, now sometimes you can ask yourself, well, what if I try to make a double bond between these two nitrogens? Well, that wouldn't really work out, because if you look at this, say I have two nitrogens and then my oxygens. So what if you ask, oh, well, what if I put the double bond between the two nitrogens? Well, that's not going to work out, because if you try to draw it out, so we said we needed 17 electron pairs. So we already used up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and 17. So if you try to double bond the nitrogens, that's not going to work out, because this oxygen only has 6 electrons, but it needs 8. So we can't have that because it needs a complete octet. So then the only way to fix that would be to take one of the bonds between nitrogen and put those electrons in a bond with oxygen. So then if we transfer those electrons, then this oxygen, we get that double bond. But then once we transfer that, there's still this nitrogen that still also has 6 electrons, and we can't have that happen. It needs 8. So the only way to fix that would be to take one of these electrons from oxygen, transfer it to make a new bond, and then we go back to one of our structures from the previous page, and we get a molecule that always has 2 oxygens that are double bonded and 2 oxygens that are single bonded to our nitrogens. So that means that we've exhausted all of the possible structures, or all the possible structures we could have moving the double bonds around. So that means that since these ones don't work, and this one is a repeat of the ones that we did on the first page, that means that we've only made, how many? One, this is one structure, two structures, three, and four structures. So again, the question asks how many resonance structures can be drawn for the N2O4 molecule. We have drawn 4 resonance structures. And that's our answer.